Good evening, everyone. I'm here to share the last theory topic for A-level chemistry, Singapore syllabus, Introduction to the Chemistry of Transition Elements. So these are the learning outcomes for this topic. It's a very big topic. We will spend quite a lot of time on it. So let's start with what is transition metals? They are D-block elements. So these elements are atoms where they have the inner 3D, 4D, 5D, or 6D subshells filling up based on the period they are in. So their atoms are characterized by inner buildings of these subshells. In our syllabus, we only focus on the first row of the D block elements, which are the period 4. So we focus on the 3D block, which contain 10 elements, because the 3D subshell contains 5 orbitals, each able to accommodate up to 2 electrons. All these elements involve the filling of the 3D orbitals. They are all metals and tend to be hard metals compared with the S block metals. For 3D orbitals, there are a total of 5 3D orbitals, a revise of atomic structure. We have the dxz, where the orbitals lie in the xz plane. We also have the dxy, where the orbitals lie on the xy plane. And the yz plane, we have the axis between the y and z axis. The fourth one is along the z-axis because it's above and below the x-axis, so it's dz squared. And we also have it along the x and y, x squared minus y squared. Just like what we learned in atomic structure, we use the alpha principle, Pauli exclusion principle, and the Hans rule to explain how the electrons are distributed in the orbitals. Now, as the nuclear charge increases across a period, the energy of the orbitals actually decrease. However, because of their proximity to the nucleus, the spherically symmetrical s orbitals are actually affected to a greater degree than the more angular p and d orbitals. So the energy decrease more rapidly than the other types of orbitals. So we will notice a more obvious change for the s orbitals compared to the d and p orbitals. By the time the fourth shell is reached, there's in fact an overlap between the third and fourth shell. As observed from the above graph, the energy of 4s orbital has become even less than the 3D orbital. For example, argon. Here. All right. Then the next 2 electrons enter the 4s orbital. That is the electronic configuration of potassium and calcium, which are 4s1 and 4s2 respectively. Okay, since the lower energy 4s orbital is filled before the 3D orbitals. This is because the energy of the empty 4s orbital is slightly lower here than that of the empty 3D orbitals. Starting from Scadian, electrons start to occupy the 3D orbitals. Once electrons occupy the inner 3D orbitals, the 3D electrons provide some shielding for the outermost 4s electron. This will help to repel the 4s electrons to a higher energy level. Therefore, when the electrons are being removed, because of the repulsion by the 3D electrons, the 4s electrons are removed first now as they are pushed up to a higher energy level. So these are the electron inbox diagram for the transition metal in the 4th period. Their complete electronic configuration. There are two exceptional cases, chromium and copper. So let's start with chromium. So for chromium, right, instead of having 2 electrons in 4s, we have 5 electrons in 3d because the arrangement of electrons that is half filled is actually more stable than a 3d4 and 4s2. The reason is because the 2 electrons in 4s2 are repelling against each other. So due to the repulsion, the configuration is less stable. So in order to minimize repulsions between electrons, so that electrons move to the 3d orbital for more stability. As for copper, we have a fully filled 3d orbital. So by right, we thought that this electron going by the trend as above should be in 4s. So 4s should have 2 electrons going by the trend. However, in the case of copper, we have a fully filled 3d orbital, as the fully filled orbital is actually more stable. Again, the reason has to do with the repulsion between the electrons in 4s. As we have mentioned, when the 3d orbitals electrons are filled up, the 4s, because of the shielding effect, are pushed to a higher energy level. So electrons are removed from the 4s instead from the 3d. All right, due to this reason. So when we are writing the configuration for ions, do bear in mind that we should remove the 4s electron first before the 3d. For example, iron becoming iron plus, it should be 4s1. Iron 2 plus, then 3d6. 3 plus, 3d5. Chromium 4s1, the 1 electron removed from 4s first to form chromium plus, and then we start to remove electrons one by one from the 3d orbitals. Okay. For this question, the question was asking what are the possible subshells X and Y. So they already mentioned that this element is a transition element in the 4th period. All right. So what could be the next energy level be? So because of repulsion between the electrons in between the electrons of 3D and 4s, so the 4s electron are pushed up to a higher energy level. So 3D is actually lower once the electrons are filled up in 3D. Shielding effect. Then the next question was the electronic configuration of the +1 ion of atomic number 29. So remember to remove the electron from 4s first and not from 3D. Next, transition element is a d block element as observed earlier, which can form one or more stable ions with a partially filled d subshell. So this is a definition of transition metal. However, there are exceptional cases like scandium and zinc. They are not transition elements since they do not form any stable ions with a partially filled d subshell. They only form Sc3 plus and Zn2 plus. So we do not have it forming more than one stable ion. All right. For example, scandium, they remove these two, 3p6. Zinc, remove this. So not all the d block elements are considered transition metal based on the definitions. Okay. So the ions of these two actually do not have the partially filled d subshell. All right. One is fully filled d subshell, one don't even have d subshell after the ions are formed. The element copper forms Cu plus, okay, which has a fully filled d subshell. But can copper still be considered? Yes, because other than copper plus, copper can also form copper 2 plus with a partially filled d subshell. All right, so it depends on whether it can form possible ions that fulfill the definition of a partially filled d subshell. The first row transition elements are all metals, and they are similar in physical properties, like they are hard compared to group 1, they are soft. They are high densities compared to group 1 is low density, high melting and boiling point compared to group 1, low melting and boiling point, and they are good conductors of heat electricity. due to the availability of the delocalized electrons. As for atomic radius, they are almost constant, not exactly constant, but almost. Because if we look at the nuclear charge and shedding effect, as across the period, the number of protons increases, which increases the nuclear charge. The number of electrons also increases. So electrons are added to the inner 3D subshell. So the inner 3D subshell will share the outer 4s from increasing nuclear charge. So the increase in shedding effect, due to the increase in number of 3D electrons, will help to offset the increase in nuclear charge due to a considerable extent. To a certain extent. So why do I mention considerable extent? So meaning it can offset a bit, but not a lot. So there will still be a small increase in the effective nuclear charge, and attraction for valence electron remains relatively constant. And the atomic radii will be relatively constant, is often regarded as constant. So some of the first row transition metals readily form alloys with each other, partly because they have similar atomic radii. All right, so they can mix more easily. So the first IE of the transition metal, just like the atomic radius, is almost constant, almost. So just like previous reason, the first IE of the transition metal is almost constant because the electron being removed comes from the 4s orbital. Across the period, proton number increases and thus nuclear charge increases. The electrons across the period added to the 3D subshell. The inner 3D electrons share the outer electrons from increasing nuclear charge. So the increase in shedding effect due to the increase in number of 3D electrons across the period offset the increase of the nuclear charge to a considerable extent. So the effective nuclear charge only increases slightly. All right. So the energy required to remove the first electron is almost constant. If we compare the S block and transition metals, the melting point of the transition metals are definitely higher than the S block within the same period. Reason being, valence 3D and 4S electrons of the transition metals are close in energy. So both the 3D and 4S electrons are available for delocalization into the sea of electrons. So we have more electrons available, which strengthen the metallic bond. For example, this is a standard question, why titanium has a higher melting point than calcium, though they are in the, they are similar in the same period, right? That is because, right, titanium has a higher melting point due to stronger metallic bond, require more energy to break. The stronger metallic bond arises due to titanium cation having a higher charge density, okay, because compared to calcium, it does really have a higher nuclear charge, all right? And then both 3D and 4s electrons are also available for delocalization, which actually increases the number of electrons in the sea of delocalized electrons, which strengthen the metallic bonding. Comparing S block and transition metal, the transition elements in general are denser. That is because transition metal have a smaller atomic size, but a larger atomic mass compared to S block. So we will expect more atoms to be packed per unit volume for transition metals. As for density, right, there is a gradual increase across the period because the atomic radius is almost constant, but the mass increases, which explain the gradual increase in density. Now look at chemical properties. Transition elements form compounds in which the transition element shows a variety of oxidation state. However, for S block element, they only exist in compound with a fixed oxidation state. Another difference between them is transition metal usually form colored compounds as well as ions. Okay, but for S block elements, they are quite boring. They are usually white in solid state and colorless in aqueous solutions. Transition metal also have catalytic activities, both the element and the compound they form. So they can be homogeneous or heterogeneous catalysts. We have one classic example in the Haber process where we use finely divided iron. However, for the S block element, we do not have any of their elements or compounds showing much catalytic activity. The reason is because they themselves are very reactive, so they will tend to participate instead of increasing the speed of reaction. Transition elements show a great tendency to form stable complexes. All right, but we don't really see much with the S block elements. The reason why stable complexes can be formed is because they have empty 3D orbitals that can actually accept electrons from the ligands, where it's absent in S block. I mean, S block do have, but it doesn't have, it's not so strong, not so stable compared to the transition metals. So transition elements and variable oxidation state. So these are some of the examples. Why are transition elements able to show variable oxidation states in their compounds? Because 3D and 4s electrons are very close in energy level. So when bonds are formed, it can involve electrons from the 4s and the 3D electrons. For example, chromium can form Cr2 plus by losing one electron from 4s and the other from 3D. In which it exists in a low oxidation state of +2. However, in the case of CrO42 minus, we can see that Cr assume a high oxidation state of +6 because it's able to utilize all the 3D electrons and 4s electron, which is a total of 6 electrons in covalent bond formation. Because of the close similarity in energy of the 3D and 4s electrons for the first row transition metal. So consider the IE of calcium and vanadium as shown below. The graph for vanadium shows that the first 5 successive IE of vanadium increases rather gradually with no distinct large increment. But we do not see that in calcium because for calcium, we can see a great jump in IE between the second and the third. Because the third and fourth electrons of calcium, which are in the inner principal quadrant shell, is nearer the nucleus quadrant shell and experience much greater nuclear attraction and require much more energy to be removed. Now, the table below summarizes the known oxidation numbers of the elements, okay, across the period. So in general, the highest possible oxidation state is equivalent to the number of unpaired d electrons and the 4s electrons. So for example, cobalt, okay? Cobalt have 3 unpaired d electrons. So you need to know how to draw the electron inbox diagram to identify how many unpaired d electrons are there and how many 4s electrons are there. So if you take this, okay, so these are 3. Then these are the other 2. 3 plus 2, 5. So the maximum oxidation state of cobalt can go all the way to +5. The number of available oxidation state of the element will actually increase from scandium all the way to manganese. Okay, the value of the maximum oxidation number for the element suggests that each element or the available 3D and 4s electron may be used for bonding. From manganese all the way to zinc, we notice a decrease in the number of oxidation state exhibited by the elements. So we can see that the most common oxidation state for each element include like +2 or +3 or both. The lower oxidation states are usually found in ionic compounds. Such compounds tend to be reducing agent because they oxidize itself very easily. The D block element can be oxidized to a higher oxidation state. Okay, The higher oxidation states, right, tend to include covalency and electronegative atoms, such as fluorine and oxygen, and can be found in polyatomic oxo anions like BO3 minus, CrO42 minus, MnO4 minus. Such compounds tend to be oxidizing agent, as the D block elements can be reduced to a lower oxidation state. Okay. Because of the ability of the D block element ion to be oxidized to a higher and lower, so they have different properties lah. Oxides of elements in a low oxidation state tend to be basic as they are ionic, while oxides of elements in high oxidation state tend to be acidic as they are covalent. All right, so some of it is they can change according to the oxidation state of the element in that particular compound. So this exercise is unlikely to exist. So if you look at this titanium, they have, if you draw out the 3D, so you have 3D, I only draw to 3D, 4S. So you can tell that the number of available electrons is 2 plus 2, 4. So 2 unpaired 3D electrons and 2 4s electrons. So if you look at the oxidation state of each compound, here is plus 3, and plus 2. So these are possible, but plus 6 is a bit too much for this. So this is unlikely to exist because the maximum oxidation state of titanium can only be 4. Okay? Plus 4. Now, for redox system involving transition metal ions, we look at the relative stability of different oxidation state will be best understood in terms of standard electrode potential. Okay, so we look at the reducing equation. The more positive E0 value, which will indicate that the equilibrium position will tend to lie on the right-hand side. So the plus 2 oxidation state is favored over the plus 3 oxidation state if we have a more positive E0 value. Going across the transition elements, there is a general increase in E0 value for reduction of plus 3 to plus 2 oxidation state. There's a dip in E0 value from Fe3 plus to Fe2 plus. Okay, that is because the addition of electron to iron 3 plus result in a 3d6 configuration. Okay, that is going to cause some inter-electronic repulsion between the paired electron in the same 3D orbital. So reduction of Fe3 plus to Fe2 plus is less favored because of the repulsion between electrons in the 3d6 configuration. Aqueous KMnO4 acidified with dilute acid and aqueous potassium dichromate acidified are common oxidizing agents, as we can see them in redox and organic chem. So based on the E0 value, we can tell that MnO4 minus is a stronger oxidizing agent compared to Cr2O72 minus. So we can actually use E0 as a way to gauge the strength of the oxidizing agent. So we have reviewed what is catalyst in the topic of kinetics. I shall not elaborate much on it. We also talk about the difference between heterogeneous versus homogeneous catalyst. So something that you can read yourself. And some of the examples have been covered before in the various topics earlier on. All right. So in heterogeneous catalysis, right, the catalyst and the reactants are in different phases. The catalyst is usually in the solid phase as it provides sites. We call them active sites. where reaction take place and reactants are usually liquids or gases. For heterogeneous catalysis, the reactant molecules has to be readily absorbed on the catalyst surface. Such type of catalyst is a surface effect, which involves the formation of weak attractive force between the reactant molecules and the atoms of the surface of the catalyst. All right? So this is absorb, not absorb. Okay? The molecules do not go into, okay, the catalyst. It is still on the surface, forming some kind of attractive force between it and the catalyst itself. Now, because of the partially filled 3D subshells, they allow for ready exchange of electrons to and from reactant molecules, which facilitate the formation of weak bonds with the reactant molecules. So the availability of the 3D electrons for bond formation with the reactant molecules, or the availability of low-lying vacant orbitals, allow them to accept electron pairs from the reactant molecules. Okay? So they either use the 3D electrons to form bonds with the reactant molecules, or the catalysts use their orbitals to accept electron pair. So they have this flexibility there. So this is the mechanism of what happened during heterogeneous catalysis. So the reactant molecules will first diffuse towards the catalyst surface. Okay, so the reactant molecules will start to approach, come nearer to the catalyst surface. All right, so this is a very typical hydrogenation reaction you learn in organic chem. Alkenes reacting with hydrogen using nickel as a catalyst. So nickel is the heterogeneous catalyst to provide the surface for the reactant molecules to come together. So the reactant molecules will then become absorbed onto the active site of the catalyst by means of attractive force. So this absorption will lead to an increase in reaction rate because the bonds within the reactant molecules in the process are weakened, which reduces the activation energy. Also, the reactant molecules are brought into close contact with the correct orientation with the help of the nickel providing the active site. And then, because they are in the correct orientation, the adjacent reactant molecules are brought into close contact. This reaction has a lower EA than uncatalyzed reaction where the molecules are may not bump into each other. Okay, they may not collide with the correct orientation. So these catalysts actually provide an opportunity, okay, for the correct orientation to be met, okay, and allow them to react. So upon reaction, we have the desorption where the product molecule form will break free from the catalyst surface. The product molecule will diffuse away from the surface and allow the vacant active site to be available to absorb other reactant molecules. For homogeneous catalysts, the mechanism works a bit differently. Instead of providing the surface, we don't really talk about active site here. Okay, so the catalyst and the reactants are in the same phase, either liquid or gaseous. So with the help of the catalyst, let's say CT is the represented symbol. So A will first react with the catalyst to form an intermediate product. And this intermediate product is able to react with B to form the desired product and releases the catalyst, which can be used to react with another reactant molecule. Okay, so the mechanism is very different, whereas the homogeneous catalyst, right, in the same phase as the reactants, right, will participate directly by reacting with it. But in the heterogeneous catalyst, right, it will just be providing a surface for the correct orientation of reactant molecules to be adjacent to each other so that the reaction can proceed with a lower EA and hence increases the rate of reaction. So a typical features of homogeneous catalysis is the catalyst take part in the reaction by being converted into an intermediate compound. And this intermediate compound will subsequently undergo reaction to produce the product and allow the catalyst to be regenerated. All right. So the larger activation energy for the uncatalyzed reaction in this case will be replaced by two smaller EA for the catalyzed reaction. Meaning the reaction takes place in two steps. There are two elementary steps now. But it is good because it creates a new reaction pathway with a lower EA and increases the speed of reaction. So instead of having one large EA, we have two smaller peaks. All right. The enthalpy change remain unchanged because you are still talking about the same reaction. So what are the important features of transition metals which enable them to function effectively as homogeneous catalysts? Okay, number one, they can exist in different oxidation state in compounds, and the relative ease with which they can be converted from one oxidation state to another. I think this is something that we have gone through in the topic on kinetics. So, but we will talk about E0 value here. Okay. This reaction is not the same as this, so do not be confused. All right. For uncatalyzed reaction, right, these two, as we have talked about it in the previous topic on kinetics, right, it's very difficult for them to react because these two ions are of the same charge. So there will be repulsion between them, which makes reaction difficult to proceed. So very high EA will be required. Sorry, this reaction will have a very high EA. So you really need the reactant molecules to be at very high energy for the reaction to proceed. Although based on the E0 cell value, right, if you take 2.01 minus away 0.54, so you choose this reaction, right, it's actually a positive value. It looks thermodynamically feasible under standard condition, but kinetically speaking, cannot. So we will need the help of Fe3 plus to catalyze the reaction, okay? So with the help of Fe3 plus, so this time around, we will focus on the E0 value. In kinetics, we don't really talk about it. So we have the Fe3 plus to react with the I minus first. Okay, it's pretty easier compared to the negative ion because they are opposite charge. So they are likely to come closer and react, right? And this is the E0 value of Fe3 plus. We will just take 0.77 minus 0.54 because we have I minus become I2. Okay, so it's positive. Then we have the Fe2 plus that form from step 1 to react with your S2O82 minus with the peroxyl disulfate. That will be 2.01 minus 0.77. Okay. So you take the half reactions that is reduced minus the one that is oxidized. Okay, always like that. Okay. So the catalyzed reaction proceeds via two-step route. For each step, the E0 cell is positive, indicating that yes, the step is thermodynamically feasible. Each step involves a reaction between opposite charge ions, so they have a natural tendency to attract each other, which helps to lower the EA and enhances reaction rate. Okay? But if you have Fe2 plus, it can also work. Yeah, it can also work either way. It will still give the same result eventually. Doesn't matter. Yep. Now, let's start with the concept of complexes. One of the most important chemical properties of this topic on transition element is their ability to form complex ion. The ability actually is not confined to the transition element. We do see non-transition metals like aluminium and even iodine to form complexes. All right, lead as well. So it's not a characteristic that is restricted to transition metal. All right, but we see it quite common with transition metal. So what is a complex ion? A complex contains a central metal atom or even an ion linked to one or more surrounding ions or molecules, which we call them ligands, by dative covalent bond or coordinate bond. If the species carries an overall charge, it is called a complex ion. So for complexes, the number of bonds formed with the metal ion exceed the oxidation state. All right, so we have more bonds forming. All right. For example, like CuCl2, right? We cannot call it a complex because you see, the oxidation state of copper is +2, but we only have 2 bonds. So the number of bonds correspond to the oxidation number. Therefore, this is not a complex. But CuCl2 minus is a complex because here the oxidation state of copper is not +2, it's +1, but we have 2 bonds. So the number of bonds exceed the oxidation state. They must exceed, not equal, must really exceed. So some important definitions and key points. So there are other, but there are examples of neutral complexes. It's possible, like these two, and complex ions like these three. Okay, and this is how the diagram looks like. So for example, iron with cyanide, right? So iron is itself is actually 2 plus, but each cyanide is 1 minus. All right, so 3 plus, sorry, 3 plus. Each cyanide is 1 minus. So overall is 3 plus. So how do you get the 3 minus here? Is this one is +3, this one is -1. Cyanide is Cm minus 1, Cm minus. So you need to take note about that. So you have +3 plus -6 give you -3. That explains how the -3, the overall charge was derived. And make sure that when you show the dative bond, it's pointing towards the iron because the iron has low-lying vacant 3D orbitals to accept electrons from the cyanide. And make sure you show the 3D shape, like 4 cyanide on the plane, 1 on top, 1 below, at least. All right. So the coordinate geometry is octahedral because if you join them together, it's 8-figure shape. Okay, ligand. Ligand is an ion or molecule which contains at least 1 atom bearing a lone pair of electrons, which can be donated to a low-lying vacant orbital, in this case, the 3D orbitals, of the central metal atom or ion, forming a co-coordinate or dative covalent bond. So that will form the complex. So these are the common ligands that will be tested. Based on the definitions, ligand act as Lewis base because it's donating its electrons. All right, it's electron pair. The central metal atom or ion accept the electron pair is defined as Lewis acid. Okay, coordination number is the total number of coordinate bonds. So in this case, it's 6 because we have 6 ligands bonded to the central metal ion here. A complex species can be either neutral, cationic, or anionic, okay, depending on the ligands. All right. So these are just some examples. Okay. We also have solids that contain complex ions. They are known as complex salts. They do exist as well. Like this. So the net charge on the complex ion is the algebraic sum of the charge of the central metal ion and the total charge carried by the ligands. For example, I think I showed a brief just now, right? So you have, let's say, this is +1, then this is 0, so it's still +1, okay? This is +2, this is -1 times 4, so give you -2, +2 minus 4. This is +2, then this is -6, which gives you -4. This is +3, then ICN is -1. This is 0, so you have 3 minus 1 give you +2. Okay, so here are some more practices you can try at yourself. Okay, no time to go through. Now, the types of ligands. Ligands are classified according to the number of coordinate bonds that the ligand can form with the central atom of ion. So for monodentate ligands, they are one that form only one coordinate bond. Then means tooth. A monodentate ligand is so-called since it has only one tooth, to which it attaches itself to the central cation in the complex. So these are examples of monodentate ligands: Cl minus, OH minus, Cn minus, H2O, HN3, C triple bond O. So these are examples of monodentate ligands in the complex. All right, we have shown some of them. Bidentate ligands is one that form two coordinate bonds simultaneously with the central metal ion, like all this. Okay. So examples, wow, very complex. We have this one is this one form two bonds, but it can form a total of six. In this, this is the most stable structure. This one also two. Okay. C2O42 minus. So this one is 3 plus. All right. This one is just following this to get the charge. Hexadentate means it forms 6 coordinate bonds simultaneously. Okay. So you just have to just roughly know that it exists. Yeah. Quite a lot. 1, 2, 3, 4, 5, 6. Here is 1, 2, 3, 4, 5, 6. Yeah. So it's very complex. So I will not 1, 2, 3, 4. But actually, you just have one ligand. Yeah. It's the same one. This is only one ligand. Yeah, it exists. So it's 2 plus so what charge? Minus 4. Yeah, that's why you get this. Because it's minus 4 here. EDTA. Yep. So a polydentate ligand is one that form more than one coordinate bond with the central metal ion. So we call it polydentate ligand, starting from bidentate, tridentate, hexadentate. All right. The complex ions which are formed between polydentate ligands and cations are known as chelates or chelated compounds from the Greek word chelos or crack, chlor. All right. Now, complex formation. Okay, so what are the conditions required for complex formation? So how do complex forms? All right. Of course, you need the presence of ligands, which are species with at least one atom having a lone pair of electrons to be donated to the central metal ion or atom to form the coordinate bonds. Of course, you need your central metal ion that is capable of attracting the lone pair of electrons from the ligand and accommodating a lone pair of electrons in its low-lying orbitals to form a coordinate bond. Now, why do transition metals show a high tendency to form complex? Because they have vacant orbitals. They are low-lying, like a 3D, 4s, and even 4p. So they can accommodate the lone pair of electrons from the ligands to form the dative bond. And another reason is transition metal ions, they are relatively small and highly charged. Consequently, they have high charge to size ratio. We call it high charge density. So they are able to attract the lone pair of electrons easily. The high charge density, which means high polarizing power, produces a strong tendency towards covalent bond formation. Normally, metals don't really form covalent, right? But because of strong polarizing power, it can form covalent bond with the nonmetals. So in aqueous solutions, the group 1 and group 2 cations are surrounded by water molecules as shown, with the negative ends of the dipole of water molecules directed towards cations. So these cations are known to be hydrated. And we have learned in the earlier chapter in bonding this type of interaction between cations and water molecules is ion dipole interaction. In aqueous solution, the transition metal ion exists as aqua complexes. Each oxygen atom of the water molecule donates the lone pair to a low-lying vacant orbital of the transition metal ion to form the coordinate bond in general. Aqua complexes are in the form of MH2O6. So we have water as the ligand now. All right. Okay, so these are just some of the examples that they can test you. So for group 1 and 2, they usually have hydration. For transition metal, coordinate bonds, formation of complexes because of the low-lying vacant orbitals. Now, in aqueous iron 3 chloride solution, iron 3 plus actually exists as an aqua complex ion. This is the correct thing. Okay, they don't, because of the water molecule, so it forms a complex for this transition metal. Due to this high charge and small size, Fe3 plus has high charge density and strongly polarizing. So this will distort the electron cloud of the H2O molecules and in turn weaken the OH bonds in the water molecule. Okay? This enables the water molecules bonded to it to become proton donator. Because it weakens the OH bond, right? So the H can on the water is easily taken away by another water molecule. Okay, the free water molecule in the solution act as a base as it accept the proton acceptor, so base. So what happened is that because of this problem is the Fe it's highly polarizing due to its high charge density. So it can polarize, and distort the electron cloud of the H2O molecule close to it, bonded to it. Okay. So what happened is that the Fe3 plus, so what happened is that, okay, so break H come out, you form H3O plus here. So this is a mechanism of what really happened, the steps. Okay. So you have FeH2O6 plus base here, then become OH-H2O5, H2O plus. So the Fe3 plus consequently, right, undergo hydrolysis. This is called hydrolysis. The slight excess of H2O plus causes the solution to be acidic. No, the aqueous solution of most transition metal compounds such as chromium chloride, Fe3 chloride, copper 2 sulfate, and cobalt nitrate are actually acidic because of this hydrolysis process. An aqueous solution containing either chromium 3 plus or Fe3 plus ion is acidic enough to react with sodium carbonate to produce carbon dioxide gas actually, with the formation of a hydroxide precipitate. So let's see what happens if you add sodium carbonate to a solution that contains Fe3 plus. Okay, the following three equilibria are relevant to the Fe3 plus in aqueous solution. So like that. So if you continue to add water, then more and more hydronium ion form. Okay, so if you add sodium carbonate, so the carbonate will react with the hydronium ion to form carbon dioxide and water. So the consumption of hydronium ion as it reacts with a carbonate will cause the equilibrium position of reaction 1 to shift to the right because you have less H3O plus. So more H2O plus is removed. When more H2O plus is removed, equilibrium position of reaction 2 as well as 3 are also forced to shift to the right based on LCT. Okay? Consequently, it will form this, a red-brown precipitate. But the precipitate is not iron 3 carbonate. Since solution is acidic, the carbonate itself will react and will not form this carbonate. It will form the hydroxide. Okay, so a summary of the reaction. Now, so take note that only for group 2 you form carbonate, but for aluminium onwards, not metal carbonate form. The shape of the complex ion depends on the coordination number and nature of the metal ion. So if the number is 2, linear, these are monodentate ligands. 4, tetrahedral. These are the examples: square, planar, octahedral. So these are the various shapes of the complex number, which depends on the coordination number and the nature of the metal ion. You can either represent aqua complex of copper in this way or this. Let's look at structural isomerism. When green crystals of chromium 3 chloride is dissolved in water, the chloride ions in the complex are slowly replaced by water to give blue-green and finally violet. The complexes are distinguished by precipitation of the free chloride ion using aqueous silver nitrate. So there is gradual substitution of the chloride ion by water to give different color complexes, one by one. So here you have 4 water molecules in the complex, followed by 5, and then finally 6. The free chloride ions form precipitate with the silver nitrate, forming silver chloride. The complex ions are different cations, even though the ionic compounds, they are part of the same chemical formula. So they are structural isomers to this one. The cations are of different charge. Let's look at exercise 5. We have cisplatin having this formula. In the human body, one of the chloride ions of cisplatin is replaced by 1 water molecule. Okay, so the chloride replaced by the water because water has greater affinity with the platinum. What is the oxidation number of cisplatin and in the aqua complex? So yeah, you can calculate this as, because chloride itself is -1, so this is a neutral compound, neutral complex, neutral compound, so it will be +2. Here you have 1 chloride only, -1, and the overall charge is +1, so this is +2. So the oxidation number actually remained the same for platinum. Another question, like other transition element, platinum chloride combines with ammonia to form compounds. The coordination number of platinum in these compounds is 6. A formula unit of one of the compounds contains a cation and 2 chloride ions. What is the formula of this compound? So if you have coordination number 6, that means you are going to form 6 bonds. All right, so you count. This one not possible, this one not possible. Only this one because it's 4 plus. Wait a minute. This one is 6. Wait. The formula of this compound contains a cation and 2 chloride ion, structural isomerism. So what happened is that this is what happened. This is the one. So it have two chloride ions, but with this one, impossible. Because platinum 4, ma. So to maintain the platinum 4, if this is 4, then this is 3, then this is +1, then 1 chloride. Yeah. You must have two chloride ions set free. Yeah. Likewise, this one is the answer is because this one is +4 minus 2 here plus 2 ma. So you got two chloride ions set free. So you take out the two chloride to see whether you still can form the compound. Yeah. Because coordination number 6 ma. So this one 6 cannot lay. This one 6 can. This one lay. This one is 6 cannot. This one 6 cannot also. 4 and 2. Yeah. Question 3. Chromium 3 chloride combines with ammonia to form compound X, in which the coordinate number of chromium is 6. When solution X is treated with the excess or aqueous silver nitrate, only 2/3 of the total chloride present is precipitated. So if 2/3 of the chloride are free chloride, not bonded to chromium 3 plus, then the formula of the compound X, meaning, okay, by right, the coordination number is 6, right? Only 2/3. So 2/3 is free ions. Okay, 1 is not. So if the coordination is 6, it can be this because you see, because this is Cr. All right, they already say 3 plus already. NH3, so you already have 5. So this one will be Cl here. All right, that would be 3 plus minus 1, 2 plus. Then you have 2 Cl minus. Am I right? So 2/3 is precipitated. 1 here, 6 ma. You draw this right, you won't get the, yeah, you want to have +2 minus 1. Yeah, you want to +3, then you only have 1 chloride, then 2 chloride. Then is cannot balance the 6 coordinate number. This one also cannot. Okay. So structural isomerism means like the chlorine is not part of the complex but come out lah, but so they form the isomer lah. You know what I mean? So isomerism here means that the chloride is either one of the ligand or is free chloride ions. But the overall molecular formula is still the same. Yeah. Now we look at color of complexes. Oh. Transition metal compounds are frequently colored both in the solid state and in solution. So the typical colors for common ions with water as ligand are summarized below. So just take note the one in bold. Do we need to memorize the whole list? No, no need. Those take note the one in bold, that will be good enough. All right, good enough. Okay, maybe good to take note of let me highlight all this first lah. Cobalt and nickel, good to know as well. Yeah. These are the period 3 lah. Okay, so note that vacant or fully filled D subshell is associated with a lack of color. So if the D subshell is vacant or fully filled, no color. CrH2O, this one, is violet in cold aqueous solution. Green is observed due to the partial replacement of the water ligand by other ligands. Okay, FeH2O6 is pure violet. Yellowish brown color was observed due to partial loss of H plus by a water ligand, okay, which is yellowish brown for this one. This one we went through that just now already. So there are some exceptional color. So this one is no electron in 3D, so it's colorless. So occurrence of color, so this is the electromagnetic spectrum you learn in physics. White light contains all the wavelength of light in the visible region of the electromagnetic spectrum and can be dispersed into a spectrum of colors, each of which has a characteristic range of wavelength. All right. So if selected wavelength of the incident white light are absorbed and other wavelengths are reflected or transmitted, the object will appear color. In general, an object appears colored because it preferentially absorbs some wavelength of light in the visible spectrum, so that the transmitted or reflected light is richer in the remaining wavelength of the visible spectrum. So what determines the observed color of a color object? The observed color is the color due to the combination of wavelength in the visible light that is reflected or transmitted. So the observed color is usually estimated using the ideas of complementary colors. All right, so violet, then it will reflect yellow, blue, orange, green, red. So complementary is the one opposite in this spectrum. Violet, yellow, orange, blue, red, green. Okay. Each color has a complementary color as shown in the table above. A color wheel can be used to predict the color that will be seen when the absorption occurs in part of the visible spectrum. Colors that are directly opposite each other are called complementary color. Okay. For example, when white light containing a broad spectrum of visible wavelength passes through a substance that absorbs red light. Okay, so red light absorbed. So the complementary color of red is green. So the color observed will be green and its complement of red. Okay, so the observed color is said to be complementary to the color of light absorbed. So if a compound absorbs light of one color, we will see the complement of that color because the other color is not absorbed and reflected. When light energy is absorbed by a substance, the electron in the atom of ion will be promoted from an orbital of a lower energy to a higher energy level. So the atom of ion absorbing this radiation changes from what is described as ground state to excited state. There can be more than one electronic transition. So the different transitions involve the absorption of radiation of different wavelengths. And if the absorbed wavelengths are in the visible light spectrum, then the substance will appear color. All right. Why is sodium chloride colorless? Consider the ground state and excited state of sodium ions. So this is sodium ion. So when it's in an excited state, the one of the electron in 2p jump to 3s. We have a jump because it gains extra energy from radiation. So the electron can move up to a higher energy level. The excitation of electron from the lower energy 2p to higher energy 3s requires wavelength of light beyond the range of visible spectrum because the gap is really very big from 2p jump to 3s. So this is beyond the wavelength of light. The radiation from the visible spectrum does not provide sufficient energy to promote electrons in Na plus ion to even the lowest of these possible excited electronic state. Cannot. Now, we're going to look at why are there color in octahedral complexes, all right? Looking at crystal field theory. So in crystal field theory, it provides a way of determining by simple electrostatic considerations how the energy of the metal ion orbitals will be affected by the set of surrounding ligands. So in an isolated metal ion in the gaseous state, the 5 3D orbitals are of the same energy and are said to be degenerate. In an octahedral complex, the 6 ligands will approach the central metal ion along the X, Y, and Z axis. This results in electrostatic repulsion between the electrons in the 3D orbitals and the lone pair on the ligands, and hence increase potential energy. So the energy of the electron in either the 3D orbitals in a complex of N will be higher than in isolated M atom. In these two orbitals, they have greatest electron density along the coordinate axis. So electrons in these orbitals are pointing towards the lone pair of ligands and we repelled by them. As for these 3, they have greater electron density between the coordinate axis. This is along the coordinate axis, this is between. So the repulsion between electrons in the orbital are those approaching ligands are less. So the 5 3D orbitals are affected differently by the approach of ligands because of the orientation, you see. Yeah. Because these two, because it's where the ligands are, you see, the lone pair of electrons of ligands are. Okay, very close. This one is between axes, so not so much. So these 3 and these 2 are affected very differently. The orbitals are split into 2 energy levels with energy gap between them, and the degeneracy of the 5 orbitals are destroyed in complex. So in complexes, no such thing. Okay. So you have different higher energy level for these 2 and lower for these 3. Yeah. But in tetrahedral complexes, the situation is reversed. All right, the 4 ligands in these complexes approach the central metal ion between the axes. So electrons now, because 3D, 3xy, 3iz, dzxz now experience the greatest repulsion from the ligand lone pair. So they actually have a higher energy than the electrons in the 3D x squared minus y squared and 3D z squared orbitals. Okay. We look at the energy level later. Okay. So this is one word example. Okay, the answer is here already. Yeah, between x, z, these are all just the drawing of the orbitals. Okay. This one you just have to change here. You see that the x-axis remain the same, but you swap the y and z. Yeah. Page it lah. Yeah, you swap. And here you swap between y and x. Z and y, sorry. I think I should remove here. Here like that. Then here is zx squared. Here got, because it's where the lone pair of electrons or ligands are, so there's more repulsion. So for octahedral complexes, in the presence of ligands, the 5 3D orbitals of the central metal ion are split into 2 energy levels as illustrated. So the x, y, y, z, x, z are lower because of more repulsion. They are pushed up higher. Okay. So this corresponds to energy of radiation. It happened to be okay, then we'll explain the color later. These 2, right, although there is a difference in energy, but it's a small energy gap because they are all d orbitals, you see. And it happened that it corresponds to the energy of electromagnetic radiation in the visible region because it's not so big. So it corresponds to that visible light spectrum. The transition metal compounds are therefore colored because radiation in the visible region of the spectrum is of the right quantity of energy to promote electrons from the d orbitals of lower energy to one of higher energy. We call it DD transitions. And the color observed is a complement of the color observed. But how about nickel chloride? Okay, they also form octahedral. Why? Is it colored? Why is it colored? Yeah, sorry. Why is it colored? Okay, how do you explain this answer? Okay, so to explain this answer, right, there are techniques which we'll talk about it later. So in an aqueous solution, nickel 2 plus exists as an octahedral complex. The presence of water ligands will cause the splitting of the 5 originally degenerate 3D orbitals in nickel 2 plus into 2 sets of different energy level. The 3D subshell is partially filled. So the electrons from the lower energy d orbitals can absorb energy from the visible spectrum and get promoted to the higher energy. Such DD transitions are responsible for the color observed. The color observed will be the complement of the color absorbed. So these are the key points. You must say presence of ligand, splitting, must say 3D subshell partially filled, electron from lower energy d orbital absorb energy corresponding to certain wavelength from visible spectrum and promoted to the higher energy d orbital, which are called DD transitions. The color observed is the complement of the color observed. Okay. Now, what are the factors that affect the color? So it depends on the energy gap, which depends on the identity of the metal and its oxidation state, which depends on how many d electrons are present. So compounds of the same element in different oxidation state will show different colors because there are different number of d electrons and repel electrons of the ligand to different extent, which causes the energy gap between the split d orbitals to be different. So you have different energy absorbed, resulting in different color observed because different complementary color. And of course, the ligands do matter. So different ligands have different capacities of splitting the d orbitals and hence leading to different colors. Okay, so these are just some examples. Why do different transition metal complexes containing same metal ion in the same oxidation state show different color? Different ligand, right? So different transition metal complex may contain the same metal ion, but they have different ligands. The different ligands will split the d orbitals into 2 sets of different energy level to different extent. So the energy gap is different because the ligand is different. Different transition metal complexes absorb different wavelength, resulting in different colors, which are corresponding to the complements of the different colors observed. Yeah, different extent, key points, different wavelength of light can absorb. So in tetrahedral complex we mentioned just now, the situation is reversed. So the 4 ligands in tetrahedral complexes approach the central metal ion, right? Because the way the ligands are arranged is very different. They approach in between the axes because of the orientation, you see. So for octahedral is along the axis, that is the most stable structure. Tetrahedral will be between to be more stable. So electrons in the 3D XY, 3D YZ, and 3D XZ orbitals now experience the greatest electronic repulsion in tetrahedral complex. So they have an energy, higher energy. So that makes the difference. Okay? There's still DD transitions. Let's talk about ligand exchange. An aqueous solution of nickel sulfate contains this. When excess ammonia is added, there is a change in color because some of it is converted to NH, this complex. So there's actually a ligand exchange that results in the different color. Yeah, because the ligand is different. So as we mentioned, so different ligand split the d orbital into 2 sets of slightly different energy level to different extent. So the different transition metal complex absorb different wavelength, okay, and cause different color observed because different complementary. So we talk about K value here, equilibrium constant. Let's take the concentration of water to be constant using this equilibrium. For complex, remember the square bracket lah. So KSTAB is referred as stability constant. It's a measure of how stable the complex is compared to this one, the other one on the left. So the stability constant of the complex ion is defined as the equilibrium constant for its formation. The greater the value, the more stable the complex ion relative to the aqua complex. So a large value means that the equilibrium position must lie to the right. The NiNH36 is more stable than aqua complex. NH3 is a stronger ligand, and you can deduce that NH3 forms a stronger dative bond compared to H2O. Therefore, there will be a replacement by the NH3 ligands with excess aqueous ammonia added. The formation of complex ion can be regarded as competition between two ligands for the metal ions. So in general, ligands forming the complex of higher stability constant will be able to replace the one of a lower stability constant. For example, this is the lowest, this is the highest. So you have this more often, more be formed than more likely to form than this one. Let's look at one example. Describe and explain what happens when dilute aqueous ammonia is added to aqueous solution containing copper 2 plus. So copper 2 plus aqueous is actually aqua complex. So ammonia, we know that it will form a light blue precipitate. We learned in QA in O level. Excess ammonia, you form dark blue solution, right? We also learned that earlier. So you form this. Okay. There is a replacement of complexes. NH3 replaces, because NH3 is a stronger ligand. So as we know, aqueous ammonia is a weak base that contains hydroxide ion. So the aqueous solution containing CO2 plus is blue because of the aqua complex. When you add aqueous ammonia, a blue precipitate of copper hydroxide is formed first, since the ionic product of copper 2 hydroxide will exceed the KSP. So this is how you explain. To explain precipitate, right, you need to mention about KSP. Precipitate is formed when the ionic product exceeds the KSP. Okay? So you need to also understand where the OH minus come about from the dissociation of ammonia in water. So this react with hydroxide. So first process is this OH minus replace the H2O to form this first. Okay? Or you can just simply write this. With excess ammonia, there will be a ligand exchange reaction. So you have 4 ammonia replacing 4 water molecules. So the equilibrium position of reaction 2 actually lies much to the right. As the formation of more stable, the complex is favorable. NH3 is definitely a stronger ligand than water. So the displacement takes place. The formation of the complex results in a decrease in the concentration of Cu aqua complex. And hence, what happens is that when the concentration of this decreases, it decreases the ionic product. So when this decreases, okay, because it formed, anyway, this decreases, correct? It decreases the ionic product. And ionic product will become lower than KSP. So the blue precipitate, because this decreases, shift to the right, to the left. Or you can say when this decreases, equilibrium will shift to the left. So the precipitate dissolves. And it forms this. Okay. So in this case, there exists 2 competing equilibrium, 1 and 2. Both NH3 and OH minus compete to combine with CO2 plus. But with so much excess ammonia, okay, the formation of this complex is more favorable than the precipitate. So the following equation is sometimes used to represent the dissolution of the blue precipitate upon addition of aqueous ammonia in excess. So the OH minus is come out in a way. Overall equation, this one. Now, let's look at one example question. Describe and explain what happened when EDTA is added to part 1. So you know that EDTA is then powerful. Okay, let's see. When aqueous EDTA, because it's the K stability is quite high. So when aqueous EDTA is added to a deep blue solution, okay, the color of the solution will lighten. There is a ligand exchange reaction taking place. The hexadentate EDTA will replace the NH3 and water to form a more stable copper EDTA complex. That is a light blue solution. Okay, so the following equilibrium is established and equilibrium position shift lie more to the right. So ammonia come out, water come out, replaced by EDTA totally. All right. So the above reaction is entropy favored because you are forming more aqueous particles. Yeah, so it's entropy favored also. And the formation of the EDTA complex is also more favorable. Yeah. Do they have the color of EDTA? Oh, yes. Color is here. They will give you lah. This one will give you, I think. Yeah. Next example. What happens when you add concentrated hydrochloric acid to a solution of aqua complex? So the aqua complex is blue because of this, the complex, aqua complex of copper. But with concentrated HCl, it turns green as there's ligand exchange reaction because the Cl minus will replace the water to form this. Yeah. So it will become, okay, it will form yellow. It will be yellow actually. Yeah. Then the presence of both the blue and yellow, because it's a mixture, blue, yellow will appear green. If you add more HCl concentrated, you will increase the Cl minus concentration. Equilibrium shift to the right further by LCP, so it will turn more to yellow. If you want to reverse, you can just add more water to reverse the color change. Okay, next one is one of the fascinating, intriguing demonstration of different ligand for a particular cation is outlined using silver ion. So you can have different color reversible. Yeah. So for example, you add the ligand is water, but you add more Cl minus from colorless, it become a white precipitate. You add NH3, you replace the Cl, it form a colorless solution again, and add KBr, because the silver will react with Br minus, form the cream precipitate. You add this one, thiosulfate, then you form a color solution again. You add Ki, yellow precipitate, add Cn minus, it becomes colorless again. Very interesting. Add sulfide, sodium sulfide become Ag2S is a black precipitate. Add EDTA, colorless again. So very cute. It keep on changing. Yeah. But if you go down the table, the ligands are increasing in strength and become stronger competitors. So EDTA is the best. Being uncharged, right, also means that they are less readily hydrated by water molecule. So you will need to add something else to have a reaction. Yeah, you need to add like all this instead of just, because when they form the precipitate, they are already uncharged. So they cannot be easily like hydrated by water molecules. Cannot form ion dipole interactions in that case. Another example here. So these are some stability constant for the reaction. Okay. Then you are rewrite the above equation for the case of this, write the expression KSTA, the stability constant, and state the unit. So you just write, if you want, Fe3 plus because it been reduced to 2 plus. Wait. M plus. Yeah, 3 plus becoming still 3 plus. Yeah, no change. So yeah, M is still 3 plus. So just copy and paste here. Yep. Then you have this. Okay, just write it. Part 2, predict what will be the predominant complex form when a solution containing equal concentration of SCM minus and CM minus were added to solution. You will form CM minus is, wait a minute. CM minus is a stronger ligand as seen from the table. So you'll form this one instead. Then the next question is, if Fe3 plus CO3 plus with CM minus, will be CO because larger K is stability. Yeah, that's how you do it. Okay, so these are just some real life example. Exchange of ligand in hemoglobin. So the body of an adult containing about 4 grams of iron, 75% is in the form of hemoglobin. So hemoglobin is a red pigment, red blood cell. It transports oxygen and have iron 2, which has a coordinate number of 6. So these are just the ligands. The iron 2 exhibit hexal coordination. 4 of the coordination sites are taken up by nitrogen from a ring system of porphyrin, which act as a tetradentate ligand. So it's just one ligand but form 4 bonds. Heme. This complex is called heme. Okay. Above the plane of the ring is a 5th nitrogen atom acting as a ligand. This atom is part of a complex protein called globin, hemoglobin. Okay. So the oxygen molecule can become here reversibly bonded at the 6th site here, allowing the hemoglobin to carry oxygen from one part of the body to another. Better ligand than oxygen can bond strongly and destroy the oxygen carrying capacity of the hemoglobin. For example, carbon monoxide and cyanide, they are better ligands than oxygen. So this is a schematic representation of heme, water, oxygen. Okay. Now, replacement of the water ligands in the aqua complex by other ligands can cause large changes in the electrode potential values. So value effect of CM minus ligand on Fe2 and Fe3. Okay. Replacing the water ligand by Cn minus causes the E0 value to become less positive. So become cyanide, and then Fe3 part become less oxidizing. It reduces less easily. So there is a stabilization of the +3 oxidation state relative to the +2 state of iron by the cyanide ligand. Okay. So it's energetically easier for the positively charged Fe aqua complex of iron to accept electron, since opposite charge, because it's attracting, it's called opposite charge to electron, so it's easier for it to attract electron. But energetically difficult for FeCN6 to accept. There will be repulsion. Okay, so how do you show that this Fe cyanide complex is actually a weaker oxidizing agent? You have one experiment with Ki. So 0. You just use the E0 cell value. Okay? So this one with iodide, meaning this one is reduced, so oxidize this one. The E0 cell is 0.23. You just take so 0.77. So this one is oxidizing. So minus away the one that's oxidizing directly. to this one. Okay, so the E0 cell is positive. Reaction is thermodynamically feasible under standard conditions. Brown solution of iodine will be formed. If you have this, so cyanide is plus 0.36. Okay, the one that is being reduced is here, the oxidizing one. Remember reducing minus oxidizing, we learned that in the electrochemical cell. Okay, so you take this minus 0.54. Well, this is the one that is oxidizing. Okay, then you have minus 0.184, which makes it thermodynamically not feasible. This is one proof. NH3CN minus, they also affect cobalt. So the E0 values show that there's stabilization of cobalt 3 plus with respect to 2 plus by the NH3 and cyanide ligand. Yeah, because because the E0 value lower. The cobalt aqua complex cobalt, right, is so strongly oxidizing that they react with water to produce oxygen. But these two, they are so strongly reducing, they are oxidized by air. It's the opposite lah. Okay, you can look at the reaction here to see. So this one can here, this one be like that. Reduce, minus, minus, minus. In summary, the typical reaction undergo by transition metal ions are like this two, the QA handout lah. We have learned in QA already. This one I will not go through. Other reaction is the ligand exchange reactions. So prediction of whether such reaction occurs is based on given relative stability constant of the complex ion. All right. So on and so forth. Redox reaction. Justification of whether redox reaction can always based on E0 value. Calculate the E0 cell lah. Okay. Other reactions like the hydrolysis of aqua complex can occur as well, where you have the where you have a slight excess of H3O plus making it acidic. Or you can have the okay, something like that. Then this one also will H plus from this and this reversible. Appendix wise, you can read at your own time, like the different ligands. Yeah, just a summary. All right. So thank you very much. This will be the last time sharing this. All the best for your revision. Bye. Thank you. Remember to subscribe to my channel.